Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in as we go through everything you'll need to know for next week's test. So next week's test covers statistics and probability, and we will start off with statistics. So statistics is just the collection of an analysis of data. Data is just information. You can collect data on anything you want, people's eye color, how many hours a week they exercise, whatever. So data comes in two different flavors that we've learned about. So the first is categorical, also known as qualitative data. So that's when the data you receive is a category or a word. The other type of data is numerical or quantitative, and that's when the data you receive is in numbers. So the way that you distinguish between these two, think about it if your data was phrased as a question. So what do I mean by that? So let's say I wanted to collect data on people's eye color. So pretend I'm asking the question, what is your eye color? Would the people respond with a category or would they respond with a number? So if I say, what's your eye color? You're not going to say the number 5. That'd be stupid. You're going to say like blue, green, brown, or whatever. So that's a category. So therefore, that type of data is categorical. So an example of numerical, let's say I ask people how many siblings they have. They're not going to give me a category. They're not going to say Australia. They're going to give me a number like 2, 3, 4, whatever. So that is an example of numerical data. So we need to make sure when we're collecting data that we do it properly. When we're collecting data, we want to make sure that we avoid bias. So when we're collecting data, if we collect from the whole population, we call that a census. So census is when you ask everyone in the population the question. So if I'm collecting data on eye color, then a census would be asking everyone in the population what is their eye color. If I ask just some of the population, then I am asking a sample. So for example, let's say I wanted to know what percentage of people have certain eye colors in Canberra. I want to know what percentage have blue, brown, whatever. So the population of Canberra, what is it, like between 350 and 400,000. I wouldn't want to do a census because that would take way too long. Instead, what I'd do is ask a sample. I'd ask just some of the population. So it's important that I ask a good number of people. I don't want to ask just 2 people. That'd be crazy, right? So I want to ask, say 1,000 people or whatever. It's important to avoid bias. It's important that my sample is representative of the population. I want to get the same results from asking these 1,000 people that I would get if I asked, all 380,000 or whatever it is people in Canberra. So the best way to do it, or one of the best ways to do it, usually you want a random sample. So in my example, a random sample would mean that anyone in Canberra has the same chance of being picked to be in my sample. I pick the people randomly. You know what that means. So an example of a biased sample, if I just ask, say, people with light skin, I would get biased results because people with light skin are more likely to have blue eyes or green eyes, i.e. light-coloured eyes, than people who have dark skin. You very rarely see someone with dark skin that has blue eyes. So asking just people with really light skin, that would be an example of a biased sample. That sample wouldn't give me results representative of the population, and I would very likely get different results if I asked everyone in Canberra. We also have to make sure that the question we ask is not biased. So, of course, it's hard to lie about eye color, but let's say I was asking people over the telephone. If I just said, what is your eye color? They're probably going to tell me the truth. But if I said to them, given that blue-eyed people are better looking, given that blue-eyed people are better people, they might be more likely to tell me they have blue eyes. So I've asked a question that sort of entices them, it leads them towards saying they have blue eyes. And that's what I want to avoid. Another example would be, let's say I wanted to find out the favorite supermarket of people in Canberra. Again, I don't want to ask everyone in Canberra. If I just stood outside Woolies and asked people, that's a biased sample, because those people shop at Woolies, they're more likely to say that Woolies is their favorite supermarket. An example of a biased question would be if I said, given that Woolworths is the best supermarket, what is your favorite supermarket? That would be biased because I'm leading the people towards a certain answer. So we've got to make sure that the questions we ask and the samples we take are not biased. We've got to make sure that samples are representative of the population. If they are, the samples allow us to make inferences about the population. So let's say, for example, that I asked 1,000 people their eye color, and let's say that there were, say, 280 people said they had blue eyes. If my sample is not biased, I can use this to estimate how many people in Canberra as a whole would have blue eyes. So let's say that there are 380,000 people in Canberra. I'm not exactly sure how many there are, but let's just say there are. So all I need to do is take that number and times by the proportion of people who had blue eyes in my sample. So assuming my sample's not biased, this is how many people I would expect to have blue eyes in Canberra. Now, if I put that on my calculator, I get the number 106,400. So I'm estimating from my sample that 106,400 people in Canberra have blue eyes. And we could have done that, with any data set. If I say ask people their favorite supermarket, as long as I don't have a biased sample or have asked a biased question, I can assume roughly the same proportion, same fraction of people in my sample who said they like Woolies. That's the same as the proportion of people throughout Canberra who like Woolies. Okay, now we're going to look at the analysis of data. So please pause and copy this down if you need. Okay, so let's say I asked a small number of people how many minutes per day they exercise. So let's say I just asked 6 year 8s. Now that wouldn't be sufficient to be representative of the whole year 8 population, but nevertheless we're going to analyze this data. So if I ask people how many minutes per day do you exercise, they're going to respond with a number. So this is numerical data. So we can only calculate mean, median, mode, and range for numerical data. You can't calculate the mean eye color or the median eye color. That doesn't make sense. So we'll go through how to calculate each of those things. So to calculate the mean, remember you add up all the scores and divide by n, which is the number of scores. So here, if we add up all the scores, we get 174 divided by 6, because there are 6 scores, so that means 29. So the median, remember, it's the middle score, but the scores have to be in order from smallest to largest. So I'm going to quickly do that. So from smallest to largest, the scores look like this. Now, when you have an even number of scores, as we do here, 6 scores, then we have 2 middle numbers. So the median is halfway between those 2 numbers. So if you're not sure which number's halfway between 14 and 17, you just take the average. So you just add them up and then divide by 2. So the median here is 15.5. The median number of minutes of exercise per day is 15.5. Calculating the mode is the easiest. The mode is just the most common. So you can have no mode. If no scores are repeated, you can have more than one mode. And here we have 2 scores that are most common, 14 and 17. So we write them both down. Now, all of these 3 things, mean, median, and mode, they're measures of center. The point of them is to summarize the middle of the data to give us an indication of a normal score. That's what they're there for. The range, on the other hand, is not a measure of center. It tells us how spread out the data is. And the range is simply the highest score minus the lowest score. So in this case, it would be 100 minus 12, which is 88. Now, I know some people have been told different things, so I need to clear this up. When we're calculating the mean, median, mode, or range of a data set, we can't just ignore the outliers. We don't just exclude them from the calculations. But I'm now going to recalculate the mean and median without the outlier so I can show you what happens. Firstly, we need to know what an outlier is. So an outlier is basically an observation that's unusual. So it's either much larger than all the rest or much smaller than all the rest of the scores. So in our example above, 100 would be the outlier because it's much larger than the rest of the scores. So I'm going to recalculate the mean, not including that score of 100. So if I don't include that score of 100, they add up to 74. There's 5 scores, so the mean is 14.8. If I recalculate the median of those scores, so once again, I'll put them in order. So it'll be 12, 14, 14, 17, 17. So when you have an odd number of scores, the median's easier to calculate. It is just the middle score. In this case, the median will be 14. Okay, so what I wanted to show you is look at how much the mean and median changed after I took out the outlier. So the mean went from 29 to 14.8. It basically halved, whereas the median didn't change much at all. Now, this isn't just an accident. This isn't just true of this example. The mean is more susceptible to outliers. That means it's either dragged up or dragged down by very large or small observations. That's because when you calculate the mean, you include all the scores in your calculation. When you're calculating the median, it doesn't care what the largest or smallest scores were. It only cares about the middle scores. So that's why the median is less affected by outliers. So the mean changes a lot when there are outliers. So for that reason, sometimes the median is a better measure of center than is the mean. An example of this would be when people report on house prices. They always report the median house price, and that's because for houses, there are some outliers. There are a few houses in Australia that are just really, really expensive. They drag the mean up. So the mean isn't that useful. It doesn't give a good indication of a normal house price. The median, which is basically unaffected by those really expensive houses, gives a better indication of a normal house price. All right, that's all for statistics. Let's move on to probability. Okay, so hopefully you know that probability is basically the mathematical language of chance. You can talk about chance without referring to much mathematics, but then it becomes hard to compare the likelihood of events. So is it more likely today that it will rain, or that Mr. Lark will say yell at his class, maybe because they did something stupid like yell out Australia again? So that's hard to compare which is more likely. So with probability, what we do is we put the chance of an event into numbers, and then it makes it really easy to compare. Hopefully you remember that probability is just assigning to each event a number between 0 and 1 to indicate how likely it is. So I don't care whether the probabilities you give are a fraction or a percentage or a decimal. It's all the same stuff. But whenever I say what is the probability of something, you must give me a number between 0 and 1. You can't have an event with probability 2 or -1 or whatever. So as the probability of an event gets closer and closer to 1, the event is more and more likely. As the probability of an event gets smaller and smaller, closer to 0, it becomes less likely. It's more likely that the event will not happen. And of course, if an event has probability half, that means it's equally likely to occur or to not occur. So how do we actually calculate this number that we give events? So that's from the formula that's written here, NE over NS. So this formula says the probability of an event is the number of ways that the event can occur, And NS, S stands for sample space. It's the number of elements in the sample space or the total number of outcomes. So we use this formula when all outcomes are equally likely, okay? So I'll give you a simple example. Let's say that we roll a die, okay? So the probability of getting a 4, which we write like this, P of 4. So all the things on a die, all the numbers are equally likely to come up. There's 1 4 out of 6 in total, so we're done. The probability that I say don't get a 4, there are 5 ways it can occur. I could get a 1, 2, 3, 5, or 6 out of 6 in total. The probability I get a number that is at least 4, greater than or equal to 4, I could get a 4, 5, or 6. So that would be 3 ways it can occur out of 6 outcomes in total. All right, next thing we need to look at is the idea of complements. Again, please pause and copy down the slide if you need. So the complement of an event is just that event not happening. So here we're using the word complement as in goes together rather than complement like I say you're a great guy. So let's look at some events and their complements. So the event that it rains today, the complement of that is that it doesn't rain today. We usually just put that dash there, which means not. So let's say I'm thinking about my sports team winning on the weekend. The complement of that is not losing. It's not the opposite of the event. The reason that losing isn't the complement of winning, because if I don't win, I could lose or draw. So my team wins on the weekend. The complement is they simply do not win on the weekend. So let's say I have the event that I pick an ace out of a deck of cards. The complement is I don't pick an ace out of a deck of cards. I pick some other card. So the important thing here is that the probability of an event plus the probability of its complement equals 1. Probabilities add to 1 in the exact same way that percentages add to 100%. So you know this is common sense, you know. If the probability that it rains today is 30%, then the probability it doesn't rain today is 70%. And the same works for probabilities. If the probability my team wins on the weekend is 0.62, the probability that my team doesn't win is 1 minus 0.62 or 0.38. Notice that this number and this number add up to 1. So if I pick a card from a deck, the probability that's an ace is 4 out of 52 because there are 4 aces and 52 cards in a deck. So the probability I don't get an ace is 1 minus 4 over 52 or 48 over 52. And note that this and this add to 1. Okay, so complements can be very useful when we're determining probabilities. So for example, if I toss 4 coins, the probability that I get 4 heads, you don't have to know this, I'm just going to tell you, is actually 1 over 16, right? So if I want to find the probability that I get at least 1 tail, I can use this idea to find that out quickly. So if the probability that I get all heads is 1 over 16, the probability I don't get all heads is 15 over 16. And note, if I toss 4 coins, the events that I get 4 heads and that I get at least 1 tail, they're complementary, because getting at least 1 tail is the same as saying I don't get all heads. So complements can be very helpful in probability. The last thing we need to go through is Venn diagrams and two-way tables. So again, please pause and copy down if you need. So in maths and probability in particular, we often refer to sets. So set is just a collection of objects. You can have the set of prime numbers or whatever. I'm going to do an example with a set of students with blonde hair and set of students with blue eyes. So what Venn diagrams and two-way tables do, they give us a good way to display information. They give us a good way to write conveniently how many members are in each set or both sets or neither set or whatever. Okay, so I'm just going to make up random numbers for this example. So let's say I have 12, 7, 21, and 60. Okay, so in a Venn diagram, there are always 4 numbers. They correspond with 4 possibilities. So in this case, the sets are blonde hair and blue eyes. So there are 4 possibilities. So you could have a student that has blonde hair, but not blue eyes. You could have a student that has both blonde hair and blue eyes. You could have a student that has blue eyes, but not blonde hair. Or a student that has neither blonde hair nor blue eyes. So this Venn diagram just gives us a way to display the information. And when it does that, it becomes easy to answer questions regarding probability. The probability that a student is in one set or both sets or whatever. Okay? So this middle bit, students that have both, we say that they are in the first set and the second set. Okay, so whenever we're talking about and, we're talking about people in the middle there. Okay, so all of these students here that are inside the circle, they are the students who have blonde hair or blue eyes. Now in maths, when we say something is in, set A or set B, we really mean it's in A or B or both. When we say a student has blonde hair or blue eyes, we really mean the student either has blonde hair, has blue eyes, or has both. Okay, sometimes people get or and mixed up. So or means either one, and means both of them. Okay, before we answer some probability questions, I just want to show you a two-way table. So two-way tables in Venn diagrams do exactly the same thing. They both give the same information about members of sets. So I can convert this Venn diagram to a two-way table easily, and I'll do that now. So the reason we call them two-way tables, there are 2 directions. So across one way, you have information about one set, and the other way, you have information about another set. So the 2 sets here are blonde hair, blue eyes. It doesn't matter whether I put blonde hair going down or going across. So there are 2 possibilities with hair. They can either have blonde hair or they do not have blonde hair. And the student can either have blue eyes or not blue eyes. Now in two-way tables, we usually have a row for totals. Okay, so there are 4 cells that correspond to the Venn diagram. So this cell here, this one here, all these ones I'm highlighting in blue, those 4 numbers correspond to the 4 numbers from the Venn diagram. So in this first cell here, blonde hair and blue eyes, that's the number in the middle there. So we put a 7. This cell here, it is not blonde hair, but blue eyes only, this number here. Okay, and then we have 12 here for the number of people that have blonde hair but not blue eyes, and here we have 60 for people that have neither. So I'll just draw up the totals really quickly. So we've got 19 and 81, and 7 and 21 gives 28 and 72. These 2 numbers and these 2 numbers should add up to the same thing. Otherwise, you've done something wrong. And fortunately for us, they both add up to 100, okay, which is the sum of all these. So from this, we see that there were 100 students who were asked their eye colour and hair colour. So we can answer some questions about this. So if I pick a student at random, it has to be a student at random. So what's the probability that they have blonde hair, okay? So people often think, looking at a Venn diagram, oh yeah, cool, 12 have blonde hair. Well, it's not 12, it's 12 plus 7, because these 7 are also in the blonde circle. So the total number of people with blonde hair is actually 19. So 19 out of 100 in total. Okay, so the probability is someone has blue eyes but not blonde hair. So that's easy because of our Venn diagram and two-way table. So there were 21 people We can see that on the two-way table as well, out of 100, okay? So what's the probability that they have blue eyes and blonde hair? So that means they must have both. So that's just 7, which is this cell here, 7 out of 100, okay? So the probability that they have blue eyes or blonde hair, so as I said before, it's these three numbers here. All those students have either blonde hair or blue eyes or both, and that is these three numbers here in the two-way table. So 7 plus 21 plus 12, which gives you 40 over 100. So again, you can simplify this if you want, 2 over 5, or you can write it 0.4, 40%, I don't care. So the last thing, and I'll do top left-hand corner, what's the probability a student has blonde hair or blue eyes, but not both? Okay, so you might get a question like that in your test, and I apologize for my handwriting. So now we'll find the students who have blonde hair, blue eyes, but not both. So these students have blonde hair, but not blue eyes. These students have blue eyes, but not blonde hair. So I'm only looking at those students. I'm not including the 7 this time. So there are 12 students who have blonde hair, but not both. 21 students that have blue eyes. So that's 33 over 100. Can't simplify that further. So in the Venn diagram, it corresponds to these two cells here. Okay, so answering those probability questions was easy because we had the Venn diagram and two-way table. The last thing I want to do is give you an example, a worded example, where we have to draw our own Venn diagram or two-way table. So let's look at this example here. Group of 44 students, 24 play AFL, 21 cricket, 12 play neither. So we've got information about two sets, people who play AFL, people who play cricket. So this probability question would be quite difficult without a Venn diagram or two-way table. So we're going to draw those up to display the information in a convenient way. So first we'll start with the Venn diagram. So the Venn diagram always have a rectangle and two circles that represent the two sets. So the two sets here, as I said, AFL and cricket. Now, hopefully you're sitting there asking yourself, well, what's going on? 24 plus 21 plus 12, that's 57, but there were only 44 students. So the way that that's possible, the only way that's possible, is if we've double counted 13. We counted them in the AFL group and the cricket group, so however many you're over goes in the middle, 13. So 24 students play AFL. I've already got 13 in the AFL circle there. So that means I need 11 more to go there. So there are 24 who play AFL. Similarly, I need 8 here. So there are 21 in the cricket circle. And then 12 that play neither go outside. Now, hopefully you see 12 plus 8 plus 13 plus 11 does in fact equal 44. So we know we've done something right. Now, you could just as easily have drawn up a two-way table. So we would have two sets. So either they play AFL or don't play AFL, and they can play cricket or not play cricket. Okay, whether you use a Venn diagram or two-way table for this doesn't matter too much, okay? But it's good to have some different tools to answer the same question, okay? And we'll put a row for totals as well. So, number of people that play AFL cricket, as I said, the number of people who play both is just however many you've overcounted, 13, because the numbers added up to 57, which is 13 too many. And so there are 21 people who play cricket in total. We also know that there were 24 who play AFL and 44 in total. So I can figure out the rest of the numbers really easily. So there must be 20 here, because 24 plus 20 is 44, 11 here, 8 here, because 13 plus 8 is 21. This number has to be 23, because they add up to 44, and then that leaves 12. So whether or not you prefer the Venn diagram or two-way table doesn't matter. So to answer the question, the probability that someone plays AFL or cricket but not both. So in the two-way table, we're talking about these people. They play AFL but not both, cricket but not both. So there's 19 in total. On the Venn diagram, AFL or cricket are these three numbers, but we don't want to include those who play both. So either way you look at it, there are 19 in total out of 44, and that's our final example. Once we had the Venn diagram and two-way table, the probability question was so easy, and that's why they're important to know. All right, I hope you've got something out of this video. Best of luck for the test. This has been the luckiest maths teacher in the world. Have a great day.